Here's maybe a more real-life example where we can apply this optimization to solve a very applied problem. More than just understanding the shape of the graph of some function, we can make some choice or decision about how to build something. So we have the situation described here is we're going to have this rectangular field, and the field is going to be x long. There's going to be a semicircle on either end. Now if the radius of the semicircle is r, then that means that all the way across this is going to be the diameter. That's going to be 2r. So our goal is to make a track that's 400 meters all the way around, and what we want to do is choose the dimensions x and r so that we get the biggest possible area of the playing field in between. So the first thing we want to do is to get an expression for the area. Now the area is just going to be x times 2r, or 2xr. Now normally, to maximize something, what we need is a function of just one variable. We've got x and r. However, we can also see that because the perimeter has to be 400 meters, there's a relationship between x and r. So if we think about the perimeter, if you're going to run around this track, you're going to go the distance x twice, plus you're going to go around this half of the circle and that half of the circle. So by the time you've run the whole thing, you've gone all the way around a circle of radius r as well. Now the circumference of a circle of radius r is 2 pi r. We know that's got to turn out to be 400 meters, so we get this condition. Let's see, in this condition we could solve that actually for r. Let's see, 2 pi r has got to be 400 minus 2x. There's a 2r in this problem. I want to replace it, so if I just divide by pi, I have 2r is 400 minus 2x, all divided by pi, which I can then substitute in here, and I get the area as a function of x alone. Since the area is x times 2r, and we know that 2 times r is 400 minus 2x all over pi. Now we have the area as a function of x alone. Okay, now looking at this function, I can tell that this is, if I multiply it out, it's going to be a parabola, and the leading coefficient is going to be minus 2 pi x squared. So our function is going to be this parabola that's opening down like this. Now, it wouldn't make any sense for x to be less than 0. So first off, I know that x has got to be greater than or equal to 0. In fact, really greater than 0, but that would be sort of an extreme case to make it make the area, the rectangular part of the field, nothing. Okay, on the other hand, we can't go too far with x, because let's say x got up to 200 meters. If it was 200 meters this way and 200 meters that way, you wouldn't have any length left to go around the circle, so you'd have to make the radius be 0. So there's also a maximum value of x at 200 meters. So there's a maximum end here. You can't make x bigger than 200. So what we have is a continuous function on a closed bounded interval. We can go anywhere from 0 to 200. So so if we want to find the largest possible area, we should look for a critical point somewhere in between, right? Check the critical points and the end points. So I'm going to find dA dx. So looking at this, I could use the product rule. You take the derivative of the first, which is 1, times the second, which is 400 minus 2x over pi, plus the first, which is x, times the derivative of the second. Now the derivative of 400 minus 2x over pi is negative 2 over pi. So we get negative 2 over pi. So we find, let's see, these have a common denominator of pi, so I have 400 minus 2x minus another 2x would make minus 4x all over pi, and I set that equal to 0. And I find, if I multiply by pi, 400 minus 4x has to be 0. And so 4x has to be 400, so x has to be 100 at the critical point. Now, we just follow our procedure here. We check the area when x is at the critical points and endpoints. One endpoint we argued was 0, and of course the area there is 0. The critical point in between, there was only 1, and that was at 100. If we plug in 100, we're going to get 100. 400 minus 200 would be 200, so 100 minus 200 over pi. And then our last one is going to be at 200, right? So we plug in 200, x is 200, but then 2 times 200 is 400, 400 minus 400 is 0, so the area is 0 again. We figured that, right? If we made it 200 yards on each side of the rectangle, then there wouldn't be any radius left, and so there wouldn't really be any playing field left. Okay, we can see easily that this is the max. So what are we going to do in order to achieve that max? Well, we're going to make x be 200 meters, or sorry, x be 100 meters, because when x is 100, that's when the max is. And then we can figure out what r needs to be. From this equation, we see that 2r is supposed to be 400 minus 2x, so if x is 100, 2r is going to be 200 over pi, and so r is going to be 100 over pi. So we'll have to make the radius 100 over pi meters. That will give us the biggest playing field that we can have in terms of area with a 400-meter track around the outside.